Hi, everyone. Welcome back. This is a really exciting lecture because we're going to be talking about the Mississippi River specifically for this entire lecture, a whole lecture dedicated to just the Mississippi River. I even alluded to it a lot in the last episode, or the last lecture, where we were talking about rivers in general. But to do one specifically on the Mississippi River for us is very important because when you kind of look at a map of Louisiana, if you look at a map of even the whole Gulf Coast and you see how much sort of Louisiana sticks out into the Gulf of Mexico, how much of South Louisiana there is past sort of the I-10, I-12 line that runs east-west through South Louisiana. Everything south of those interstates essentially would not be here if it weren't for the Mississippi River and deposition of sediment at the mouth of that river. So the Mississippi River, over not just recent history and human history, but through millions of years of geologic time, has really sort of formed and created Louisiana. So for us, it's extremely important. So we're going to do a whole lecture just on the Mississippi River. Let's start by recapping a little bit from last time about the Mississippi River's drainage basin. The Mississippi River is a huge river, a tremendous volume of water, therefore of huge capacity to move sediment. And the reason for this is because of the size of its drainage basin. So the Mississippi River drains parts of 31 states out of the 48 continental U.S. states. So it's definitely the largest river in North America. And in terms of volume of water, it's one of the top 5 largest rivers in the world. So the Mississippi River is essentially draining everything from the Rocky Mountains to the west and the Appalachian Mountains to the east. And all of that water in the form of snowmelt, in the form of rainfall, anything that's not being infiltrated and becoming part of the groundwater system is really moving into that river. By way of the Missouri River, the Ohio River, and all of those rivers' tributaries, plus the northern Mississippi River and all of those tributaries. All of that's flowing into the main channel of the Mississippi River to flow through South Louisiana. And so it's really crazy to think, but throughout most of the year, the high ground in South Louisiana is actually right next to the river and all of the natural levees along that river. And the reason for this is because the river has actually built up South Louisiana instead of eroding it down like we typically think of rivers doing. So let's look at the importance of mountain building and all of the tectonic activity that's occurred throughout geologic time and how this has shaped South Louisiana, mainly because of the Mississippi River and the Mississippi River processes. So to tell this story and to look at the history of the river and the history of South Louisiana, we have to go way back before human history. We have to go millions and millions of years before even the ancestors to modern humans walked this earth. We're going to go all the way back to 65 million years ago, where the very seeds of the Rocky Mountains in the western part of the United States started to flourish and started to build those mountains. So as we look back 65 million years ago, this is a map, and these series of maps were created by someone named Ronald Blakey at Northern Arizona University, and they show us sort of an idea of what North America looked like at various points in the past. This is what North America looked like at the very end of the Cretaceous, right as the dinosaurs were going extinct. So the first thing that you might notice is that sea level is really high at this point. The sea level is far higher than it is today, and the reason for this is because temperatures were much, much warmer at the end of the Cretaceous, at the end of the period of the dinosaurs. The other main thing that you might notice is we don't technically have the Rocky Mountains yet. The Rocky Mountains are going to form over the next few million years. And what we have is the very remainder of a seaway that used to connect the Gulf of Mexico all the way up into the Arctic Ocean. So we have not quite a full continuation of that seaway now. We see sort of parts of Canada where that seaway is not connected in this picture. But that's in place of where the Rocky Mountains are today. So the sediment that is actually making up the Rocky Mountains is going to have been deposited at this time and then later uplifted. So now we go from 65 million years ago to 60 million years ago, and you can see the Rocky Mountains are actively forming at this point. They're forming because parts of the Pacific plate are sliding under the continent of the United States and under the western part of the United States at a really low angle, creating this uplift deep into the interior of the continent. Which is a little different from how it usually goes, where you have uplift occurring a little bit closer to the edge of the continent, like the Sierra Nevada uplift. So at this point, in places like Colorado and Arizona, we have the uplift of the Rocky Mountains. So now the stage is set at this point where you have the Rocky Mountains to the west and the Appalachian Mountains to the east for one big river to form and really sort of drain out all of that continental interior. And that river will ultimately be the Mississippi River. So now we're going to move a little bit more quickly through the next set of slides here, and keep in mind that sea level's constantly changing throughout all of this time, and that's happening because temperatures are fluctuating, but you still have the core of it, the Rocky Mountains and the Appalachian Mountains. And so the river is really sort of just starting to take shape. We're not going to be able to actually see the river itself, but you can see the effect of the deposition of sediment from the ancestral Mississippi River and other rivers as we continue to form the Gulf Coast. So as we go through the years to 50 to 40 to 25 million years, you're really starting to see the Gulf of Mexico take form. And just even very recently, in the last 20 million years or so, you're really going to see Florida start to form. Florida's a big carbonate shelf, so the deposition of more stuff like sand and gravel on top of all of that carbonate is really going to give us most of the structure of the state of Florida. So as we get up to 15 million years ago, I really want to stop at this point because you can really see the Mississippi River Valley start to form, flowing right through the sort of northeast part of Louisiana. And you can even see the state lines on this map. The northeast part of Louisiana and down to the Gulf of Mexico, and you can see some version of the Mississippi River Delta form in that place. And you see lots of other rivers, smaller rivers, but lots of other rivers also continue to form out the Gulf Coast. So as we continue to see this occur, we see the Mississippi River is still going to be the most dominant, and the Mississippi River Delta is going to be the one that really flourishes and really has the most deposition of sediment and the most extension of the continent. So we keep moving forward to 3 million years ago, and we see the state of Louisiana really come into its own. And it's all, again, because of the deposition of sediment. And the deposition of sediment from the Mississippi River and other rivers in the Gulf Coast. Now, the second to last of these images that I want to show you gives you an idea of what it looks like when it's very, very cold, when we have an ice age. Sea level is actually going to be much lower than it is now because the water in the oceans is going to take up less volume because the temperatures are colder, and you have more water locked up in the form of ice, both in the polar ice caps, in sea ice, and most importantly in continental ice. So we have sort of a very low sea level stand. The continental shelf here is where we're sort of seeing the edge of the continent. So there's a pretty big drop off right at the edge of that continental shelf. That's essentially the coastline out into the world's oceans. And then when you compare that picture during the Ice Age with lots of ice on the continents to what it looks like now, you're going to kind of see that difference in the continental shelf appear. So those particular two pictures, those last ones, we're going to use a little bit later when we talk in more detail about ice ages, and we're going to talk about sea level change. But for now, let's just focus on the Mississippi River. We've seen it build South Louisiana step by step over millions of years, progressing to a modern state. And we can see how the deposition of sediment at the mouth of the river is very, very critical. So What we found out by studying the river is that the way it's going to most effectively build out a coastline is to change its course. And even throughout relatively recent time in geologic time, so not talking about millions of years ago, but just talking about in the last 10,000 years, we know that the river has changed its course many, many times. So the mouth of the river is going to change its position to various points along the coast of South Louisiana. Even at one point, Lake Pontchartrain itself was a delta of the Mississippi River, but it is no longer so. That sediment has subsided down, forming the Lake Pontchartrain. Other parts of the Louisiana coastline are effectively sort of doing the same thing right now. It's natural for the part of the coastline where the river is connected to be the part that's the most uplifted. The other parts of the coastline are going to experience some degree or another of subsidence. And then the river is going to then change its course to flow to the straightest, the deepest point to flow out into the Gulf of Mexico. It's essentially taking the easiest path to the Gulf of Mexico. So the current route of the Mississippi River, where it's flowing through South Louisiana past what's now modern-day Baton Rouge and New Orleans out to the Mississippi River, started around 900 A.D. So that's only about 1,100 years that it's been flowing in its current path. And we know that over hundreds and over thousands of years before that, it's taken many, many different routes. So this graphic does a really great job of showing you all of the different routes that the river has taken over various points in history. So even just before 900 AD, we know that the river was taking a different path, filling out sort of what's now the area south of New Orleans near Grand Isle. We know that at various points thousands of years ago is tending to take a route that was taking it due south and other routes. So it's building up all of this marsh and building up all of this sediment. And then once it's built up to a certain degree, it then becomes harder for the river to maintain that current course than it would be to switch courses. So it then therefore switches course and flows in into a part of the coastline that's already deeper, that's already experiencing subsidence. So the river has essentially done this. It's changed its course. It's changed where that delta is, and that delta is where this sediment is going to be sort of the most needed at any given time, up until the 20th and 21st century, where we've begun to sort of take hold of the river and have some control in where it's going to outlet and where that delta is going to be. Now, the reason why we need to maintain some kind of control on the river is because Baton Rouge and New Orleans are heavily populated port cities that depend upon the Mississippi River, were constructed intentionally on the river itself to serve some purpose. So it's very necessary for us to be able to keep the Mississippi River flowing past those cities and not allow it to avulse, so not allow avulsion to occur and change its course, even though the river essentially very much wants to do that. So a really good example of this, an example of the river sort of wanting to change its course, is what the river has started to do and has been sort of in a very slow process of trying to do for about the last 500 years or so. So another river that plays a big role in all of this is the Red River. Long ago, it actually flowed directly out to the Gulf of Mexico and was a completely isolated river from the Mississippi River. But it actually became easier over time for the Red River to flow directly into the Mississippi River, become part of its overall drainage basin, and then all of the tributaries on the Red River, that all becomes part of the Mississippi River's drainage basin as well. So in the first of these pictures, showing the geomorphology of the Mississippi River and the old river and how that's changed to the new structure, we have the Red River and the Mississippi River as completely independent from each other. Now, Once the Mississippi River changed its course, slightly, becoming more meandering over time, which we know that all rivers, especially mature meandering rivers like the Mississippi River, tend to do, the Mississippi River began to sort of commandeer the path of the Red River. The Red River then flowed into the Mississippi River. And what's really interesting is that then the lower part of the Red River became its own almost distributary of the Mississippi River. If a tributary is where the water's flowing into the river, we know then a tributary is where the water's flowing out of the river, a distributary. So it's sort of like the Red River is essentially still there, but it's connected to the Mississippi River. The Red River flows in, and then the Atchafalaya River flows out. So this was fine for a little while these still became sort of separated streams in a sense, and the Mississippi River wasn't yet trying to take over the path of the Atchafalaya. But modern engineering of the river combined, engineering and antiquity of the Mississippi River combined with the river's natural inclination to take the fastest, shortest route possible to the Gulf of Mexico has led to the river trying to take over more and more and more of the Atchafalaya River and abandon more and more and more of the ancestral Mississippi River. So we see this particularly in the late 1800s, the early 1900s, leading up into the 1910s, the 1920s. We have a separate Red River, Atchafalaya River, the Mississippi River, and then there are these sort of connections between the two. And more, particularly during flood events, water from the Mississippi River was actually taking the path into the Atchafalaya River. So what we have now is a set of engineering structures in place that actually keep the Mississippi River almost entirely on its current path, with 70% of the flow of the river going down the normal path of the Mississippi River and 30% of the water flowing down the Atchafalaya River. So to give you a little bit of insight into how all this came to be and why this modern engineering has become necessary, even though it's extremely expensive, is we kind of have to go back to the early 1900s and look at the Great Flood of 1927 and the flooding of New Orleans, the flooding of areas surrounding New Orleans that happened as a result of that flood. Prior to the 21st century, this was the greatest flood of the Mississippi River that had ever taken place. So because there's so much damage associated with this flood, it became necessary to enact the Flood Act of 1928, and that freed up a lot of money in the United States government to actually start to create structures that would keep a big flood of this river from happening again, or at least minimize the damage from these floods from happening again. Particularly in the big port cities, the big important cities of Baton Rouge and New Orleans. So, something that is really interesting to consider here is it's not just about the old river control structure itself, which is located northwest of Baton Rouge. It's also about a series of floodways that are essentially meant to take the pressure off of the lower parts of the river by diverting some of that water out of the river itself, therefore lowering the actual flood stage of the river south of that diversion. So one place where we see this is in Morganza, Louisiana, where there's a spillway called the Morganza Spillway. And that's essentially built to take a little bit of pressure off of Baton Rouge in the event of a big flood. There's the Bonnie Carey Spillway, which is very well known. That's meant to take some of the pressure off of flooding of New Orleans by diverting water straight into Lake Pontchartrain. That was open for over 100 days this year. And then south of New Orleans, there's one that is much older than either of those, and it's called the Carnarvon Diversion. And it was meant to take the threat of flooding off of farm areas south of New Orleans. So essentially, the old river control structure was finished being completed in 1963, and since then it's actually been extremely successful in keeping the Mississippi River on its current course and not allowing it to completely dominate the Atchafalaya. So the way that this occurs is actually kind of interesting. We don't keep all of the water from going down the Atchafalaya. That would be counterintuitive because the Atchafalaya Basin is also particularly important, and the Atchafalaya River is important for cities like Morgan City. But instead, we sort of allow the river to do a little bit of what it wants to. We allow some of the water from the Mississippi River to then flow into the Atchafalaya, and then the rest into the normal course of the Mississippi. So it's really important when you're standing in awe of the amount of water that's flowing past Baton Rouge and New Orleans, that's flowing down the Mississippi River. It's important to consider that that's only 70% of its overall volume. The other 30% of its volume is traveling down the Atchafalaya River. So the Morganza and the Bonnie Carey are isolated structures that are then meant to take some of the pressure off of the cities themselves and the threat of flooding of the cities themselves. They're not so much connected with the old river control structure, other than the fact that they're all maintained by the same governmental organization, the U.S. Army Corps of Engineers. So what I'm going to do next is show you a little graphic, a little video of some floodwater from the Morganza spillway. So it's important to remember that this makes up a very, very small volume of water coming out of the Mississippi River south of the old river control structure. And as you cross over Highway 1, you actually drive right over at the Morganza spillway. This was a point when it was opened in 2011, and this is only a quarter of its overall gates open during this video. So, as I've been saying, the old river control structure is very important for maintaining that 70-30 split, having most of the water from the Mississippi River flow down the normal course of the Mississippi River, and then 30% of it down the Atchafalaya River. To give you a little bit of insight into how this actually works, we took a real field trip out to the old river control structure, where we were kind of set up near one of the lock and dam facilities. That's one of 4 facilities that's actually transferring water from the Mississippi River over into the Atchafalaya. And I got a chance to do an interview with a representative from the old river control structure. So this, I think, is going to give you a lot more insight into that facility and how important it is for really all of us in South Louisiana.
So tell us a little bit about the history of the old river control structure.
The old river control structure has a very specific purpose, and the purpose of that is to maintain the Mississippi River on its current course through Baton Rouge and New Orleans. When the river started to kind of increase water flow through the old river and into the Atchafalaya in the early 20s, it was beginning to take the more advantageous route to the Gulf of Mexico. The topography and the geography of the Atchafalaya River, it's straighter, it's shorter, and it has a better flow than the current course of the Mississippi River. So it's the natural choice for the river to take. The challenge is, if you let that occur, you'll be not only causing catastrophic damage below the old river in Baton Rouge, New Orleans, but you're also going to be causing significant damage to communities along the Atchafalaya, like Morgan City and Beulah Rose, as well as you'll be changing the entire basin. So we constructed the old river control structure to put a pause on that changing in course. In the 50s, we were at a 70-30 distribution, meaning that when you're taking the Red River, you're taking the Mississippi River, and you combine that flow, what we want to do is we want to make sure 70% of that combined flow stays through the Mississippi River and through New Orleans. And these structures allow us to do it. We operate them every day, 24 hours a day, 7 days a week, 365. The whole purpose is to make sure that the river distributions that we have today are the river distributions we have tomorrow.
So how does this facility work? What structures are in place that allow the water to divert, but not too much to divert into the Atchafalaya?
Sure. You know, when they originally built the old river control structure, there were 2 structures. There was the low seal structure and the overbank structure. 99% of the year, you would be using the low seal to pass that water through based on daily calculations. Here's what the Mississippi River is, here's what the Red River is, here's what we have to pass through. In times of flood events, we also had the overbank. And the overbank is called that because it's only operable when the water is outside its bank and it's up against the structure. In the 1973 flood, we started having significant damage to the low seal, our primary used structure. And we came pretty close to losing it in 1973. The response to that event is we built the third structure, and that's the auxiliary structure. We built that in the 80s. And what the auxiliary structure is, it has the capacity to do what the low seal does or the overbank structure. So now we have 3 structures in the complex. And then in the 90s, the hydropower plant came in and said, well, we want to be able to pass some of that water too for electricity purposes. So today we have 4 structures that are capable of being used and are being used today. And it's a daily calculation. Our engineers calculate the water, then we communicate with the hydropower plant to determine how much water they're going to take through, and then the remaining water we divvy up amongst the 3 structures to determine what that overall flow is to keep that 70-30.
That's great. That's cool. So tell us about what is happening right now, because the water level in the river is so high. It's basically, my understanding is that it's at flood stage right now. What other structures are in place, and what else has to happen in an event like this?
Sure. Right now we are in, for Baton Rouge, we're in the longest flood stage in history. We have, in the contiguous 48 states, we've had the wettest year in 124 years. The reason it's 124 years is because that's when we started keeping records. So we had the wettest year on record, and we've been in a flood fight for 203 straight days. Right, and so what we have is we have this system, and it's called the Mississippi River and Tributary System. It's a response to the 1927 flood. And what it does, unlike probably anywhere else in the country, it gives us some influence on what the river elevations will be in certain areas, as well as an overall management approach. And that has allowed us to pass previous floods by diverting water into other areas when the river system is taxed with a high water event. Today, we are passing a large amount through Old River, but we're also operating the Bonnie Carey spillway, and that is, I guess to say, creating a man-made crest in New Orleans. And then we also have the capability and may have to use the Morganza control structure. It's very similar to the Bonnie Carey, and what it does is it creates a man-made and artificial crest of the river for the communities below it, including Baton Rouge. And the system has never been fully taxed. We've never reached its full capacity. But when you're in a flood fight for 200 plus days in a row, it is under a lot of stress, it's under a lot of pressure, and we have to keep a close eye on it and operate it as it's designed to do, and that's going to be the key.
And so the Bonnie Carey and the Morganza spillway are really just to take the pressure off of potential flooding in Baton Rouge and New Orleans, and not so much to take any pressure off the Old River control structure. No,
that's exactly right. So when you're looking at the Mississippi River and tributary system, the way the system is designed is you build a levee to a certain flow, and then you build a relief valve above that levee section in the event that the water is going to exceed that flow. So for New Orleans, the levees in New Orleans are built to pass a flow of 1.25 million cubic feet per second. When we get to the point that we will be exceeding that 1.25 million, we divert water off through the Bonnie Carey spillway so that we can create that artificial crest of 1.25 million in New Orleans. The Morganza and Baton Rouge work very, very much the same way. The levees in Baton Rouge are designed to pass 1.5 million cubic feet per second. If we get to a point where we would exceed the 1.5 million, we'll divert water over into, through the Morganza into the Atchafalaya floodway. The big factor to kind of differentiate between the two is those are flood control structures. You would only ever operate them in large high water events. The Old River control structure isn't what we would consider a flood control, it's a water management. It operates every day, and its purpose is to maintain that flow. Now, as the river rises and you get high waters like we have now, well, that's going to dictate more flow being passed into the Atchafalaya River, or in this case, through the Red River into the Atchafalaya River. So it does have a relationship to the water levels, but it's not its purpose.
So at the beginning of our conversation, you talked about the old river control structure as being able to put a pause
Sure.
on this this change in the Mississippi River to want to go down the Atchafalaya. How long can that pause continue, and under what circumstances would the Mississippi River be able to really kind of take over the old river control structure and do what it wants to do anyway?
Yeah, I mean, it would be hubris on the Corps' part to say that we can dictate Mother Nature, right? I guess
But you try to all the time, right?
Absolutely, that doesn't
do.
stop us.
Yeah,
It just,
yeah.
just we're aware of it.
Right.
But I guess to say that the challenge is maintaining that distribution is not a build it and forget it type of work. It takes daily operations, it takes funding, and it takes a understanding of the river so that we can try and be one step ahead. We've been very successful. We started building it and to operate, to maintain that 70-30 split. Today we have the 70-30 split. So we're able to maintain it. If you were looking at before the structure was there, you were seeing a diversion increase by 10% every year. So every decade. So each decade you're increasing about 10%. We're holding steady, but it will take a lot of effort, a lot of work, and a lot of money.
So that interview was a lot of fun to do. I personally got to learn a lot about the old river control structure. I hope you found it really interesting as well. The next thing I want to talk about is the future of the Mississippi River, because as you've been able to see recently, flooding events in Baton Rouge and New Orleans and the threat of flooding events from the Mississippi River sort of hang over our head in a really big way. We have a big problem with this looming threat of big floods on that river, and even opening features like the Morganza and spillway and the Bonnie Carey spillway doesn't completely take out the threat of the floods to those big cities. We also have to concern ourselves with the sustainability of our coastline in South Louisiana with the river in this engineered state, because the Mississippi River isn't doing what it's sort of meant to be doing all along in switching course and changing courses and building out different parts of our coastline. So all of these things have to be taken into account when we consider the future of the Mississippi River. So keeping the river on its course is becoming more and more difficult as the river has a greater and greater sort of need and want to move down the Atchafalaya River. This can be mitigated in some amount with these freshwater diversions, which the Morganza Spillway and the Bonnie Carey Spillway are some of these freshwater diversions. The other thing that we can do is particularly in the areas around New Orleans and particularly south of New Orleans is we can have more of these freshwater diversions in place, because in addition to diverting the water in the Mississippi River and mitigating the threat of flooding south of these areas, we can also deliver some of that badly needed sediment to places in South Louisiana that are experiencing coastal subsidence and sinking. This also helps to mitigate possible problems that are going to result with the sea level rise that's projected to happen in the next 100 years as global temperatures increase, as global warming occurs. So managing South Louisiana and coastal sustainability is really all about managing the deltas and managing where that sediment is ultimately going to be deposited. Some of the forecasts for what the future of the Mississippi River entails actually has us ending the Mississippi River far, far north of where it's currently ending. So right now, the Mississippi River Delta is far, far southeast of New Orleans. And the Mississippi itself is essentially just sort of extending that river and continuing to deposit sediment further and further and further south. So by, essentially cutting off the river, maybe even as far north as English Turn, we could deliver some of that sediment to places surrounding New Orleans that really need that sediment to continue to be uplifted. And all of that marshland and all of that area that's experiencing the subsidence is really important for maintaining New Orleans itself and maintaining keeping New Orleans from the threat of big flood events, particularly those associated with landfalling hurricanes and tropical storms. So that's just kind of something to consider going backwards, going forwards, I'm sorry. And the key here is all about these freshwater diversions and their role in depositing sediment to badly needed parts of the coastline that need that sediment to continue to be uplifted. So this is a really fun lecture to do. And then the next few lectures, we're going to move on from rivers and talk about oil and gas. We're going to talk about groundwater and ice. We're going to talk about sort of other aspects of water on Earth. Until next time, keep rocking.